So this next video is now going to be on voltaic cells, and in order to know about voltaic cells, the first thing that you want to do is you want to learn a little bit about your standard reductions potential, which is this page. You should have picked it up at the same time that you picked up the rest of the unit, and what you're going to notice then is that we start out with a very high electrode potential, and a very high in the sense that it's positive. And since this electrode potential is positive, we actually know that this is going to be a half reaction that is also spontaneous. It's going to react automatically. Now notice that it is a half reaction because it only involves the one change in electrons, which is gaining of the electrons. That's, of course, why we're calling it a reduction potential, because every single reaction listed here is in fact gaining electrons. You'll also notice that as you go through the table and you get further along, we're decreasing in values, and then we come up to a 0, which is our hydrogen half cell, and then we continue to decline in negative values until you get down to the bottom. So let's talk a little bit about what that means. This table shows that anything that is listed as a reactant is easily reduced because of the fact that it has a positive voltage. So that means that the item that is most easily reduced on this table that you're looking at is the fluorine molecule. Not only does it tell you that fluorine will easily be reduced to fluoride, it also tells you that fluoride is going to be very difficult to oxidize. So you can see that we're looking at this table in both directions. The first direction being from reactants to products in terms of reduction, and the second one being from products, so in this case fluoride ions, to reactants, which would be the fluorine molecule. When you are looking at the product to reactant, what you're going to notice is that now we're talking about oxidation because we are in fact losing electrons. They're over on the right-hand side on the product side. We also know that when you do a flip like this, the voltage is also going to flip around, and so it's a negative 2.87. That negative sign is what indicates that this is going to not be spontaneous. So it is unlikely that fluoride ions would be able to turn easily into fluorine molecules again. And as we know, fluorine in general is highly, highly reactive. So highly reactive actually means that it's able to turn into the fluoride ions easily. As you then go down this whole list, what you're going to see is that means that these are becoming less and less able to be reduced. And that also means that each of these reactants are less able to act as a good oxidizing agent, right? So that which is reduced can be an oxidizing agent because it can cause something else to be oxidized. As you go down to the bottom of this table, what you're going to see is, again, we get closer and closer to negative values. So now we have a very negative 3.05, and that means that this reaction is non-spontaneous. You'll notice that the reaction is the lithium ion turning into the lithium solid. That means that the lithium ion does not want to gain electrons. Oops. So we are going to, right, this is difficult to reduce. And at the same time, if we flipped it around and looked at the lithium solid, that would mean that our lithium was in fact turning into lithium ions and releasing an electron. That would be a good, right, an easy, I should say, oxidation. And because it's a good oxidation, we know a couple of things, right? One, the value is positive as a 3.05. And two, that lithium will react with anything when it's in its solid form. If it's in its ion form, not so much. It's going to act like a neutral ion. It's not really going to be involved. It's going to tend to spectate. We tend to cross it off. But lithium as a solid will try to react with everything. And you guys have actually already seen that, right? Because lithium in water easily reacts and turns into the lithium ions. All right, so having kind of an introduction to this table is now going to help us figure out how to do the voltaic cells. So on our voltaic cells, we are looking at a couple of things. Voltaic cell means that it's a spontaneous reaction. That's really what you're talking about. And it's a redox reaction. There must be one reduction and there must be one oxidation. For all of the reactions that we're going to be doing, it's a one of each kind. Each half is going to then join together to make the entire redox reaction. Because the voltaic cell is spontaneous, we know that delta G will be negative, and we also know that K will be a larger number than 1. And as we just started seeing on that table, the voltage also needs to be positive. If those three things are, all of those three things are directly related to each other. So if one changes, it's going to impact the other two. You also saw that we selected hydrogen as our arbitrary, we selected hydrogen as our arbitrary half cell. And that means that we're making it our reference cell. It turns out that every single reaction that is a half cell is compared against hydrogen. So it's the sort of thing where we were unable to really just measure it directly. It's not an absolute value like entropy is. We had to make a comparison. So because we had to make a comparison, we always made one half cell into hydrogen and then use that to compare against each of the other half cells. Based on the voltages that were created from that, we then wrote out the reduction table in order of the potentials going from highest to lowest. So this is all relative, right? Because they're all going to be relative to the hydrogen half cell. We also saw here that if you are looking at the reduction potential, and instead you want to have the oxidation, so you flip the reaction around, you'll just go ahead and change the sign. That's going to be exactly the same way as with Hess's law for heats of reactions. If you reverse the reaction, you will go ahead and reverse the sign. And also if you add two reactions, because we're going to need to add the two halves together, you're going to just go ahead and add the voltages. The thing that is not going to change is, in fact, it's totally different from Hess's law with heats of reactions. Just because you double a coefficient, you do not change the value of the electrode potential. That's unusual, and it's because it does not matter how many moles are being transferred. It only matters that electrons are flowing through the system. If electrons flow, you get a voltage. How many electrons flow doesn't matter, okay? So we're going to start with number 5 here under these examples, and then we're going to come back and talk more about the E total as we go to the next page. Within our examples, what we want to do is we want to look at how to know if a reaction is going to take place. So we're looking at the spontaneity. How spontaneous is this going to be? And through spontaneity, we can actually define certain things. So we can say, what is the reducing agent? Is it going to be a better reducing agent or a weaker reducing agent? Remember that the reducing agent is the reactant that is actually being oxidized. So that's the first thing, right, is being able to identify with that table who's going to be spontaneous and who's going to be maybe a stronger reducing agent versus a stronger oxidizing agent. And again, remember, an oxidizing agent is the reactant that is being reduced. All right. Having said that then, let's go ahead and look at the two examples that we've got. In the first case, we're looking at tin 2 turning into tin 4. So if you notice, that means that we are gaining an oxidation number, and therefore we are releasing some electrons. That's how we know that it's being oxidized. We're also looking at iron turning into iron 2. So same type of idea. You are looking at the solid form, which has a 0 oxidation number, turning into a +2, and therefore it is releasing 2 electrons. In order to decide who is the stronger reducing agent, we want to know which of these reactants, tin 2 or iron, are going to have a larger voltage, which will represent the fact that it is more spontaneous. So the more spontaneous it is, the better it's going to act as that type of agent. All right, so turn back to this table, and we're looking for iron and we're looking for tin. Don't fool yourself in accidentally finding something like this, where the iron 2 is present, but its opposing species is iron 3. You want to have the exact same 2 species, one on each side of the reaction. So let's continue to scroll a little more. All right, now we're getting into some great stuff here. We have a tin 2 and tin 4. Notice the problem is, again, the tin 4 is written as the reactant so that it's reducing. That means that when we go and we actually want to look at tin +2 as the reactant, we need to reverse the reaction. If we're reversing the reaction, the 0.15 will be a negative 0.15. So let's go ahead and jot that down. So this voltage is now negative 0.15. And then we're going to again go back to our table and hunt around a little bit more for the iron. Here it is. So again, we want the iron 2 and the iron solid on separate sides. Again, we notice the iron solid is acting as a product in this reaction, so we're going to flip the reaction around. Because we're going to flip the reaction around, we're not going to have a negative 0.44, we're going to have a positive 0.44. So again, we'll write that down. Since that's the case, this is a pretty easy one to decide on because the voltage of iron as a reactant is positive 0.44 versus the voltage for tin 2 as a reactant, which is negative. That means the stronger reducing agent, the thing most likely to be oxidized, will be solid iron. Notice it is not the iron 2. It's the solid iron. Who is the reactant right now? All right, let's do the next one. The table that I've given you is not useful for the manganese and permanganate, so I'm going to go ahead and switch those. Let's do tin solid or tin 2. And now what we're going to do is, again, we want to find which of these reactants could be the stronger oxidizing agent, which really means which of these reactants could be most easily reduced. So again, who is going to be the most spontaneous? Our choices, if you look at your table, could be that you go from Cl2 to Cl-. You could go from Cl- to Cl2. There's a tin solid to tin 2, and of course the opposite of tin 2 going to tin solid. And since we haven't specified any kind of reaction, like we did up here where we said specifically look for tin 2 to tin 4, we haven't specified that, so let's also include the tin 2 to tin 4 as well as the tin 4 to tin 2. These are all the options that you can look at. And now we're going to just make sure that we're looking at the correct thing. Is it an oxidizing agent? Is this half reaction being reduced? So if it's being reduced, you got to gain some electrons. So we see that we're gaining electrons here. That's an option. Whereas the chloride to chlorine, we're actually losing electrons. Since we're losing electrons, that actually means that since chloride as a reactant could only give us an oxidation and lose the electrons, chloride cannot be a selection for our strongest oxidizing agent. All right, tin to tin 2 is now also releasing electrons, versus the tin 2 to tin is gaining electrons. So that means that tin as a solid, since that's the only place where it is a reactant, cannot ever be a stronger oxidizing agent. And we can remove that from our list also. Okay, we have 2 more to look at. That's the tin 2 to tin 4. If you notice, right, this particular trend is that the electrons are again being lost, so that's oxidation. Whereas the tin 4 to tin 2, your electrons are being gained. So we cannot select tin 2 in this case as a good oxidizing agent because, again, it's being oxidized, not reduced. We also cannot select the tin 4 because that wasn't one of our choices up here. So even though this is correctly being reduced, we weren't trying to compare tin 4 to the others. Okay, we now have narrowed down to 2 reactions, and so we're going to go ahead and again turn to the table. We'll start out looking for the chlorine, and again, once you find the chlorine, we want to double check that it's reduction, which the whole table is reduction. So you see that chlorine turning into chloride ions is a positive 1.36. All right, that's a really great high number, so chances are that's going to be our answer, but let's just double check with the tin 2. Again, we are looking at the tin 2 turning into tin solid, which is this one. So a negative 0.14. All right. Now you can tell that because we have a positive value for the chlorine, chlorine is going to be our answer. So it, as a reactant, will act as the stronger oxidizing agent, meaning its chlorine atoms are physically being reduced by gaining electrons.